name is Salvatore Migliaccio. I'm from Namirial, and today I've come to you with this talk about an idea on how to upgrade the blockchain into a quantum-safe one. In this talk, we will start from the very basic information about quantum computing for those of you who don't know. Then we will lean forward about what are the current vulnerabilities of existing blockchain. And then we will lean on how Namirial is going to work on this type of things. So, first of all, Namirial just want to talk about this kind of topic. That's because our main operation, our main purposes are done via current encryption, like RSA, ACC, etc., etc. Then, in this talk, we are just going to introduction to quantum computing, then the current vulnerabilities, solution, and our solution. So let's start. The first thing that I want to show you, that I want to talk to you, it is what is quantum computing and what are quantum computers. So just to be clear, just to be easy, quantum computing is just a computational paradigm that uses the principle of quantum mechanics, such as the entanglement or superposition, in order to elevate the computational power to an exponential level. When the world started talking about quantum computers, in 1980s, the first idea emerged from Richard Feynman, and later the Peter Shor, in 1994, developed an algorithm capable of breaking current cryptography algorithm. So, just to understand why quantum computer is so much powerful than normal computer, at the base there is the quantum bit, the qubit. In the classical type of way that things are done in our computer, we have the bits that are or 0 or 1, that can be in only two states. In the case of quantum computers, we have 0, 1, or a combination of those type of states. In order to elevate our computational power, we use even the properties of quantum mechanics, such as the entanglement or the superposition. So, in order to give you some sort of idea how powerful it is a quantum computer, in like maybe 5 years, 10 years, we could expect to break RSA in just a few hours, and this is such a really, really bad thing for our company, or in general for those companies that work in the classical way that encryption is made. So anything encrypted today with RSA or ACC can be archived and then cracked once a fault-tolerant quantum computer exists, or when it gains certain maturity. So, just to give you some number about how the world is moving forward and towards quantum computing, there are several industries, several companies, several countries that are now investing in those sort of things. For example, China, Russia, France, Europe, United Kingdom, Canada, America, etc. And even some big tech like IBM, Microsoft with the project Majorana 1, that is a quantum SIP that could have some of the revolutionary new class of material, etc. Google right now is working in the quantum AI, that is really, really important. Quantum AI is just the combination of quantum capabilities with AI, and then AWS with the cloud quantum computing via Amazon Braket. So, let's now dive into the main things of this talk. So, how a quantum computer could break our blockchain. So I understand that you already know what are the current vulnerabilities of blockchain, and we have a short amount of time, so I will not dive deep into that. So there are 51% attack, contract logic bugs, private key and wallet compromise, chain bridge exploit, etc., etc. But the real thing is how a quantum computer could break the blockchain. The first thing that comes in our mind is the Shor's algorithm. As I said before, Shor's could be used in order to break current cryptography. That's because it can solve logarithmic problems in a polynomial time, which is currently unfeasible even for the most powerful computer. The second thing is the Groover's algorithm. The Groover's algorithm is just a quadratic speed-up hash search on our system, so it could easily break proof of work or proof of stake, giving a majority power without having the 51% resources of the blockchain. The last things, the last threat that we want to talk is the harvest now, decrypt later. This is just a paradigm of mind where some sort of malicious actor could achieve all our transaction, all our information on the internet, on Web3 right now, and then later in the time, as I said before, could break those type of encryption and then gain access to our information. Then every used address is already exposed because if you can take the private key or the public key of a certain type of transaction, you could get all the information about this type of transaction. And then with the private key, you can fakely sign some type of transaction in order to steal our cryptocurrency. So why quantum computers have not broken our security system? And that's because quantum computers have some real problem right now. The first problem is the fragile qubit things. This type of things is that even a small amount of disturbances, quantum noise, can cause this qubit to lose their quantum properties. There is this draw that I really appreciate, that is the quantum coherences. The quantum coherences is just a sort that a qubit doesn't know where to go. It doesn't know their properties, their values. So even if we do some sort of operation, some sort of calculation, we arrive to a different complete results. The second thing is the huge overhead for fault tolerance quantum computer. That's because we need at least 1,000 physical qubit in order to get one logical qubit. Right now, in the research area of quantum computers, this type of things can be achieved in less than 1,000 qubit, but in order, in a realistic world, in order to break RSA, we at least need millions of physical qubit. I know there is the surface code definition, there is the infrastructure, the laser one, so it's not like maybe an impossible thing to reach this type of computational power. The last thing is the error correction. As I said before, the qubits are very fragile, so quantum computers need this sort of error correction code to resolve some of the serious problem. So there are several solutions to quantum computer attacks right now. There are two main roads ahead. The first road is post-quantum cryptography, that is the simplest one out of the two, because it's just a paradigm that will need to replace RSA or HEDSA with algorithms that are safe from quantum computer attacks. That's because this type of algorithms are based on mathematical problems even difficult for quantum computers, like the less-is-based one, the hash-based one, the code-based one, or multivariant cryptography. The second road is the quantum cryptography itself. So if you cannot defeat them, join them in a sort of way. So we like to apply quantum mechanics principle like the QKD or some other things of protocol like the BB84 in order to encrypt our information with quantum computers. In this way, we are safe from the attack of quantum computers because we could protect ourselves. So just to give you some sort of background on why post-quantum cryptography is so important right now, even the European Union and the NIST are working on a roadmap to migration to the PQC in order to give the data that are right now in the internet a bit of security. So how are we going to implement PQC in blockchain? There are three roads that we can follow. The first is an hybrid approach where we combine cryptography algorithm, classical cryptography algorithm with post-quantum cryptography. The second one is a blockchain fork, an hard fork of the blockchain, where we create a new version of the blockchain that only uses post-quantum cryptography algorithm, and then the protocol update. There are some problems with this sort of solution. The fact is the keys and the certificate that uses post-quantum cryptography, for example, the lithium-2, the lithium-3 algorithm, have key and certificate that are even larger than the one that we use right now, and this could affect transaction speed and blockchain size. So, our solution is a simple one, it is a mocked one right now. We are testing some other roads that we can take, some other things that we can understand, and this is just to build a signature on top of an Ethereum transaction. This type of things is done via generating the hash of a transaction, then generate a private key using a post-quantum algorithm. For example, as I said before, Falcon or the Lithium-2 tree. Denise is recommending to use the Lithium-3 as the post-quantum cryptography algorithm. Then we generate the signature, and then we can take those signatures on the chain and be safe from the attacker that tries to take our personal information on the information of our transaction. The use case for our demonstrator is just some sort of testing. We right now are not trying to implement it on the chain itself, but we are studying how it can be possible to protect ourselves in the future and right now. So, I would like to thank all of you for the attention. Sorry if my English is bad, it's not my first language. If you want to contact me, there is the LinkedIn link and the email. Thank you, everyone.